let's consider our load here connected towards the end of the line. And this load is supposed to take some power. So there's going to be some incident plane wave or incident TEM wave, as we discussed last time, propagating down this line. The transmission line will have some characteristic impedance Z0 and some propagation constant beta. Eventually, once the wave hits the load, there's going to be some voltage across the load, which is shown here as VL. And conventionally, we're always placing our loads at the Z equals 0 in our Z-axis. So essentially, the wave is coming from the negative. It's coming from here. And the beginning of the line is called, at Z equals negative L, is going to be somewhere here. Of course, the line is assumed to be infinite. So we're going to discuss later on what happens when we excite this line with a particular source. Right now, we're only worried about the termination at the other end where basically the load exists. So essentially, the incoming TM wave, as we discussed last time, is going to have some type of a magnitude, V0 plus. It's propagating towards the positive Z direction. So it's e to the negative J beta Z, as you will see right here. And that means there's going to be a corresponding current wave, the I incident that you see right here, which of course will be equal to V0 plus divided by Z0, e to the negative J beta Z. Now, in most of the cases, in most of the real life scenarios, this transmission line is not going to be equal to ZL. So in other words, Z0 is not going to be equal to ZL. Most loads do not have the transmission line impedance Z0, which basically means that if the only thing that exists on this transmission line is this incident wave that we just discussed right here, then the boundary condition at the load will not be satisfied. Or in other words, if the only thing that exists is this incident TM wave, then the voltage at the load divided by the current at the load will not be equal to Z0. And so that reason is the main reason why we need to assume that not only the incident wave is there, but also there's going to be a reflected voltage and current wave on this transmission line. So there's going to be a reflected voltage wave that you can see here with a magnitude of V0 minus. Now this one is propagating towards the negative Z, so that means this will be e to the J beta Z. And the corresponding current wave is going to be given by negative V0 minus over Z0 e to the J beta Z. So this negative sign, by the way, simply comes from the fact that if you basically take the voltage wave and plug it into the telegrapher's equations, you will basically get this reflected current wave. So if I consider both my voltage incident waves and my voltage current, my voltage reflected waves, I'm going to get my total wave on this transmission line, incident plus reflected. And similarly, I will have the incident plus reflected current wave on this transmission line. Now, as we're going to see later on, that V0 plus that we have here is going to be determined primarily by the excitation, and that for now is going to be assumed to be known. Again, this is determined by the excitation. That means the source that will excite this transmission line. So this is more or less known. On the other hand, this V0 minus that you see here is basically our unknown. And so the main goal now that we have essentially expressed our waves is to find out what exactly this V0 minus is. And once we find this V0 minus, then we'll be able to find both the voltage as well as the current wave. So let's see how we do that. In fact, the way to do that is to apply the boundary condition of this transmission line. And the boundary condition is determined by the voltage over the current at the load position. So if I look at the ZL is equal to VL by IL as dictated by my load, then remember that my load is at Z equals 0. So I will take the expressions I had before and plug in Z equals 0. And so when I do that, that means that the voltage will be equal to simply V0 plus V0 minus. And similarly, the current will be equal to V0 plus by Z0 minus V0 minus by Z0. So the voltage is V0 minus is my unknown, ZL and V0 plus are known. So that basically means that I will be able to find my unknown voltage V0 plus as shown right here. Pardon me, V naught minus as shown right here. So V naught minus is going to be equal to ZL minus Z naught over ZL plus Z naught times the known incident voltage. Now, we will often write this as gamma L times V naught plus, where this gamma L is essentially my reflection coefficient caused by the load. So this gamma L, as is shown from this equation, is simply ZL minus Z naught over ZL plus Z naught, and I have explicitly written it right here. So what we've basically just learned, just to summarize, is that if I have a transmission line with an incident TM wave and a characteristic impedance of Z naught, and I terminate this transmission line with a load ZL, then necessarily I'm going to get a reflected wave, and the magnitude of this reflected wave will depend on this reflection coefficient gamma L, which has this very simple expression that I'd like all of you to memorize. It's simply ZL minus Z naught over ZL plus Z naught. Now, we should remember that ZL in general is actually a complex number, and that means that this gamma L in general is going to be a complex number. So it's going to have a magnitude and a phase, which I'm calling here theta. So now if I take this expression for V naught minus, and I basically express my V naught minus with respect to gamma L, I will get these expressions right here, which gives me the total voltage wave and the total current wave as a function of V naught plus and gamma L.